Oh,
Okay, so this is the demonstration of our project, and the whole demonstration will be divided into two parts. And the first part is the 200 and GF 256 and calculation, and the second part is AES encrypt and the decryption. And I will introduce the first part. And for GF 255, we made a calculator. It will actually do the basic calculation like addition, multiplication, and also get the inverse of the input value. And the first of all, we need to make sure the input value and is close, not close, is it is from 0 to 255. Okay, and then we input the value a and b, and we will return use the XOR. So that is a basic idea, and because this is a calculation and based on the a bits. So then we got the result from the addition. This is the first function, and the second function we created based on our textbook, and the input value are a and b, and the two value gonna do the multiplication, and besides we need to input the modulus, and the modulus is called irreducible polynomial, and the value is based on this power function, and the highest one is a power 8, and is x power 8, x power 4, x power 3, x, and plus 1. And so we change the value and into the hexadecimal value, which is OX11B. And then we're gonna do this operation to the value, input value A and B, to make sure they're not gonna overflow. And after that, we initialize the product, which is equals to 1, and it will go through the 8 loops. And the reason we go through the 8 loops is because of the highest value of a power, which is 8. And then we will go to the procedure step by step. And the first step actually is a invariant of the equation from the book. So A and B so can switch into the xa and plus 0 and multiply by b. And in this way, and we will actually we will actually already move a to the left. So we move a, so in this way we need to have the a0, and besides, and we need to move the a value and into the next power, so they will move right. And so this is how we design this equation. And after that, and when we have the b, we will firstly you're gonna move the b position and to the left, and then we will take a look at if the b value is 0, is b7, is the b because the b7 related to the highest power value. If the highest power value is equals to 0, okay, that's fine. And if it is a power equals 0, it is a 1, and it will go through this calculation, which is gonna multiply the irreducible polynomial, and will transfer into the value that can be calculated. And after that, the a value gonna move to the right, and after it moved right, and they will go to the next loop. So this is how we obtain the value of the product. And when we put the 87 and 171, 131, and we will have 183. And this is a second function. And for the third function here, and we create a two function, which is the first one, which is embedded. The first one is called the degree, and use a degree, and we will have the highest power value of the polynomial, and which is transferred from the decimal a. So this is how we do it. And then we will have the invert, which is which will invert any value of the GF2 power 8 except the 0, because a 0 is not okay for this invert multiplicative inverse. Okay, and then let's go through the GF256 invert. So at the beginning, we're going to input the value of a, and we're going to set the modulos, and we initialize the G1 and G2. G1 is the value we're going to have for the inverse. So we can see from at the end we will have the G1, and then there's a G2 equals 0, and G2 actually which is the value we're going to initialize as a 0, gonna accumulate step by step. So it will, based on the transfer of the value, they will actually increase the G1. So right there, and we can see we have the A. So we want A to be the GCD, and if A is not equals to GCD, and it will go through the loop. After A got a GC, after A is the 1, of course, and we will have the G1. And the theoretical background is based on the extended Euclidean algorithm to find a multiplicative inverse. And in this way, we can see, and we give it like a 2 integer, and this is a, this is a b, and this is a GCD, AB, and this is how we design. And in this case, and we have to transfer their own value, and to make sure, and the GCD is equals to 1, and the TB is right there. So NJ right here is to calculate, is to control if we gonna continue the switch, if we're gonna continue the loop. So, and if we'll work with the J, and the J value actually will eventually calculate the final inverse of the multiplicative inverse, and this is a function of inverse. And after that, we made a tester, so this is a value we have.
Okay, so for the AES functions illustration, first we're gonna show that there were no functions generated for generating the S and the inverted and X boxes, because those are specified values, and we define them as variables, so we can access each of them values and replace them and execute it, the functions that are required for the rounds in the AES encryption. So this is the first function that defines the current state of a block, that is the bytes to matrix. It converts the 16-byte array into a 4x4 matrix. So this is the function that shows the current state of the block, because it's converted into a matrix. And this function does the reverse of it. It converts the 4x4 matrix into a 16-bit array. This function and XOR bytes is a function that I define in order to fasten the process of the XOR, because we're going to do a lot of XORs in this encryption. So I define a class, and then the expand key, I didn't do it, but these are the functions that were assigned to me, that were the encrypt block and the decrypt block. So here basically first we are asserting a length of the plaintext, and we are going to set it on 16 bytes to assure it's 16 bytes, and then define the first state, that is converting the plaintext into a 4x4 matrix. And then we execute the first method established by the AES, that is the add round key. We pass the plain state, and we pass the subkey we're going to use for this method, because in key underscore matrices is an array of all the subkeys that are required to execute in all the functions that are implemented inside AES. So then it enters a for loop, and it will execute n rounds. That will be 10 because this is AES 128 bits, so it's gonna execute 10 rounds 10 times. And the first block will pass throughout all these functions 10 times. That are the sub bytes, shift rows, mix columns, and then it will add the round key of the state after the mix column method. So this and the explanation of the AES, and then at the sub bytes, shift rows, and add round key, it's then called to here, and then I print the current state of the block encrypted, and then it's returned into bytes, into byte form. So the same logic is used on the decrypt. We assert the length of the ciphertext into 16 bytes and then convert it into a matrix to define the cipher state, the first state. And then we call three functions that are required for the decryption, that are the add round key. But the difference to the encrypt is that the functions called here are the inverse of it to reverse the process of the encryption. So we call inside the for loop the 10 rounds, we call the inverse functions that are the add round key is the same, but we call the inverted mixed columns, inverted shift rows, and inverted sub bytes. And then in the final, this will execute 10 times always, and for the same block. And then for the final, it's called the add round key, and passing the cipher state and the sub key used for that. So basically, let me check if I can explain another method. Yeah. So basically, what I implemented the shift rows. Basically, what it's doing, it's shifting every row. The first row it will shift. It will not shift, but the second, the third, and the fourth will shift to the right, and the inverted will shift to the left. But the first row will shift to one time. The third will shift 2 times, and the last one will shift 3 times. The inverted does the same, but the reverse process. So sub bytes and inverse sub bytes replaces the values. The sub bytes replaces the value established by the state and replaces it with the value in the X box, and the inverse sub bytes does the inverse. Does this with the inverse X box values. The add round key just passes the state and passes the key we are going to use, and does an XOR with that state. And basically for the test functions, the methods that I explain now are the methods that I designed. So for the test functions, basically what we did is that we stored in 2 variables, the key and the plaintext, and then a variable I store the encryption, and then I print it, and then a separation to know the difference, and the encryption I store in a variable, and I printed that. So let's run it, and let's enter the key. Let's say it's hello, and this is a test. And as you can see here, this is the states throughout all the process of the 4 blocks of the 16 bytes. So you can see the difference of states throughout all the process, and then you can see the encryption here. It's very straightforward, and then the current states passing throughout the decryption phase. And as you can see here, this is the plain text that passed through the decryption. So thank you very much.